All rights reserved goes to Robert W. Sebesta, as most references and points are based from his book Concepts of Programming Languages, 10th edition. For an overview, as the title indicates, the topic is expressions and assignment statements. The semantic rules that determine the order of evaluation of operators in expressions are discussed first. This is followed by an explanation of a potential problem with operand evaluation order when functions can have side effects. Overloaded operators, both predefined and user-defined, are then discussed along with their effects on the expressions in programs. Next, mixed-mode expressions are described and evaluated. This leads to the definition and evaluation of widening and narrowing type conversions, both implicit and explicit. Relational and Boolean expressions are then discussed, including the process of short-circuit evaluation. Finally, the assignment statements from its simplest form to all of its variations is covered, including assignments as expressions and mixed-mode assignments. Now, expressions. I know you've heard of this word before because I can tell from your expression. From facial expression to mathematical expression, we'll be leaning more onto the latter, as expressions are the fundamental means of specifying computations in a programming language. At the same time, you'll be getting your assignment. Statements basically changes the value of a variable or perhaps the state of a program, which is quite a statement in imperative languages. Or you could say that it's imperative to have a statement. For this presentation, we'll go through the semantics of expressions and assignment statements, or in other words, the meaning of expressions and assignment statements of a language. In arithmetic expressions, automatic evaluation was one of the primary goals of the first high-level programming languages, and most of their characteristics are more in line with those found in mathematics, science, and engineering. In programming languages, arithmetic expressions consist of operators, operands, parentheses, and function calls. Note that an operator can be unary, which means it has a single operand, example being -4 plus 5. Binary, which means it has two operands, example being 1 plus 2, 2 minus 3. Ternary, which means it has three operands, example being if, then, else. In most programming languages, binary operators are infix, which is something that everyone is familiar with. The operators are in between the operands like 1 plus 2. However, in some languages such as Perl or Common Lisp, which their operators are prefix, which they appear before the operands like plus 1, 2, which is still equivalent to 1 plus 2. Now, the purpose of arithmetic expression is to specify arithmetic computation. On such implementation, it must cause two actions: fetching the operands, usually from memory in the case of variables, and executing arithmetic operators on those operands. Later on, we'll go through the common design details of arithmetic expressions and the primary questions regarding them. Therefore, be sure to remember these points. What are the operator precedence rules? What are the operator associativity rules? What is the order of operand evaluation? Are there restrictions on operand evaluation side effects? Does the language allow user-defined operator overloading? And what type of mixing is allowed in expressions? In operator evaluation order, the first two questions are discussed regarding the precedence and associativity rules as they dictate the order evaluation of its operators. Starting with precedence, consider this expression: A plus B times C. Let's say that the values are 3, 4, and 5 respectively. There are two ways of evaluating this in the way of directions: left to right, which the result is 35, or right to left, which the result is 23. However, instead of just evaluating the operators through either directions, this can be done to the technique that everyone would be most familiar with, which is PEMDAS: parentheses, exponents, multiplication, division, addition, and subtraction. This was long ago developed by mathematicians, the concept of placing operators in a hierarchy of evaluation priorities and basing the evaluation order of expressions partly on this hierarchy. In other words, if this technique was applied from the previous example, then multiplication is evaluated first and addition second, since multiplication has higher precedence. Now for the operator precedence rules. For the expression evaluation, it takes the order in which the operators of different precedence/priority levels are evaluated. For the expression, it is based on the hierarchy of PEMDAS in the preference of the language designer. And a side note, various languages also include unary versions of addition and subtraction. Unary addition is called the identity operator, since it is basically the positive integers that you see without the associated operator and really has no effect on its operand, example being 1, 2, 3. Essentially, it is useless. Unary subtraction, however, changes it. In most languages, the unary minus operator can appear in an expression either at the beginning or anywhere inside the expression, though some languages require parentheses to prevent it from being next to another operator. As shown, a plus b opening parentheses minus b closing parentheses times c is legal, and so is a plus minus b times c, though not in all languages. Now, here are the precedents of the arithmetic operators of Ruby and the C-based languages are as follows. For those unfamiliar to a couple of operators, percent or modulo gets the remainder of two integers. Plus plus or minus minus are called increment and decrement respectively, which just adds or subtracts the operand by 1. Speaking of which, let's proceed to associativity. Look at this expression, a minus b plus c minus d. Considering that addition and subtraction operators have the same level of precedence as they do in programming languages, the precedence rules say nothing about the order of evaluation of the operators from the given expression. In common languages, associativity is usually left to right. APL order of evaluation of operator expression is defined purely by associativity rule, specifically the right associativity, as shown a times b plus c. The addition operator is evaluated first, followed by the multiplication operator. If a were 3 and b were 4 and c were 5, then the value of this APL expression will be 27. Programmers can modify the rules by placing parentheses in the expression. Consider this expression, opening parentheses a plus b, closing parentheses times c. Normally, multiplication will be evaluated first. However, due to the parentheses, addition will be first. In a way, the first operand of the multiplication operator is not available until the addition in the parenthesized expression is evaluated. On a fun note, all arithmetic and logic operations in Lisp are performed by subprograms. The subprograms must be explicitly called, however. For example, to specify the C expression, a plus b times c, in Lisp, one must write the following expression. Opening parentheses plus a opening parentheses times bc closing parentheses closing parentheses. In this expression, plus and times are the names of the functions. However, when a list is interpreted as code in Lisp, the first element is a function name and the others are parameters to the function. Now that unary and binary had been established, its ternary turned to the limelight. In the conditional expressions, you might be familiar with the if, then else statements, as seen here. If count equates to 0, average will be 0. Else, average will have the value of sum divided by count. In some languages, like C-based ones, this can be summarized to this form. Expression 1, question mark, expression 2, colon, expression 3. Expression 1 is the Boolean expression. Results will be either true or false. Note that the question mark denotes the start of the then expression and the colon denotes the start of the else expression. If this is true, then the value of the whole expression will be the value of expression 2. If false, then it will be expression 3. So, translating the previous example to the specifying form, average will be if count equates to 0, then 0. Else, it will have the value of sum divided by count. Moving to the next issue, the operand evaluation order is not that relevant since variables in an expression are evaluated by fetching their values from memory. Same goes for constant values at times, as some cases it might be part of the machine language instruction. Remember that if an operand has a parenthesized expression, then the sub-expression will be evaluated first before the rest. For this design characteristic to be relevant is when the evaluation of an operand have side effects, which will be discussed next. A side effect of a function, also called a functional side effect, occurs when the function changes either one of its parameters or a global variable. A global variable, if you're unfamiliar, is declared outside the function/method but is accessible in the function/method. Consider this expression a plus fun a. Going back to the operand evaluation order, if there are no changes happening on a, then evaluation on a and fun a will not affect the result of the expression. However, if there is a change, then there's a side effect. Here's a C program that illustrates when a function changes a global variable. See that at the first line is the global variable a with its initial value of 5. Next set of line is the fun1 method that when called will change the value of the global variable a to 17 and then return an integer 3. Last set of lines is the main method that contains the expression which will also call/invoke the fun1 method. Now there will be two different results that can occur due to the operand evaluation order in which the operand will be evaluated first. If a is fetched first, then the value of the expression will be 8, since no changes has happened initially. If fun1 was first, then the value of the expression will be 20, since the value of a has been changed globally. To rectify this particular problem of operand evaluation order and side effects, perhaps a language designer could disallow functional side effects and also specify that operands and expressions are to be evaluated in a particular order and demand that implementers guarantee that order. However, those are not perfect solutions, as disallowing side effects would eliminate flexibility and efficiency use of data in the expression and program as well. Having a strict evaluation order will disallow some optimization methods to be used by compilers since they involve function calls and reordering operand evaluations. The Java language definition guarantees that operands appear to be evaluated in left-to-right order, eliminating the problem discussed in this section. The concept of referential transparency is related to and affected by functional side effects. A program has the property of referential transparency if any two expressions in the program that have the same value can be substituted for one another anywhere in the program without affecting the action of the program. For example, result 1 is equal to sub-expression function a plus b divided by sub-expression function a minus c. The temp variable will have the value of function a, and in result 2, sub-expression temp plus b is divided by sub-expression temp minus c. If the function fun has no side effects, result 1 and result 2 will be equal, because the expressions assigned to them are equivalent. However, suppose fun has a side effect of adding 1 to either b or c, then the result 1 would not be equal to result 2. So that side effect violates the referential transparency of the program in which the code appears. It may seem somewhat useless due to the functional side effects, though there are some advantages to referential transparency. Most important is its readability, that its semantics are much easier to understand since it's more alike to a mathematical function in terms of understanding. Therefore, functional languages are referentially transparent since the closest to mathematical functions.